All right, in this video, it says for approximately what values of x can, I think that's a typo. Can we replace sine of x by this with an error magnitude no greater than 5 times 10 to the negative 4? Now, we actually did this graphically in the last video, but we need to use the remainder estimation theorem. So this is not a graphical way of doing it. It's a much more theoretical way of doing it. And so it's a little tricky, especially if you're in my class, and I didn't really get a chance to do one like this because we didn't have time. So you can just watch this video and follow the steps, and maybe it'll help you a little bit in your future. It says use the remainder estimation theorem and view that as the 6th degree rather than the 5th. So that's a little strange comment. You might say, like, why would we do that? So just one thing to notice. Let me just remember, sine of x can be represented as this infinite Maclaurin series and like you notice all of the even degrees are gone, etc. All the even degrees are gone. So like if I said write down the 5th degree polynomial, that's what you see above. Right? Just stop at the degree 5. It's also the 6th degree polynomial, and that's because if you just note like what's not there, like there are all these zeros that we could put in front, right? So like I could write this if I wanted to. Like plus 0x to the 6th. Right? Like you could just think of the coefficient of the degree 6 term being 0. And so like why would you do that? Really just in this specific problem you do that because it tends to give you a little bit more precise of an estimation of your error. Like there's nothing wrong with using thinking of your polynomial as a degree 5, that'll work. But if you use a degree 6, you actually get a little bit more accurate statement. So I guess the metaphor would be like you have to get work done in your car, and the mechanic's like, well, it won't cost you more than $500. And then like he calls you back and says, I just talked to the supplier, and I just, I got the parts. It's not going to cost you more than $435. Like the second, both of those were true originally, or both those statements are true. It's just that once you got more information, the second one's a little more precise, right? And a little more helpful. So that's kind of why you would use it as a degree 6. Okay, so with that in mind, let's use this formula and then see what it looks like. Okay, I'm going to move that down. Okay, so here, let's just note what things are. So we're using, so n's now going to be 6, right? N is our degree. We'll deal with m in a second. X is, we're going to leave that blank because we're actually looking for a range of x values. So we're going to get this inequality that we're going to basically solve. A is the center. This is clearly centered at 0 as we can tell. And then there's an m, right? So remember, m is the maximum, or a maximum, of the n plus first derivative. So if we're using n, it's the maximum of the 7th derivative on the interval 0 to wherever you're doing your approximation. So we don't really know. We don't have a particular value we're doing our approximation. But the more important thing is let's just find the 7th derivative of sine. Do that pretty quickly. So sine is the 0th derivative. The first is cosine. The second is negative sine. The third is negative cosine. The fourth is sine. The fifth is cosine. The 6th is negative sine. The 7th is negative cosine. So what's the max of, or give me a maximum value for negative cosine? Well, these sine and cosine graphs don't go above 1. So you can use 1. So let's just use 1. Okay. All right, and so let's see. Now what? Let's plug everything into this equation. All right, or inequality rather. So it's going to be our error. So our n is a 6. The error when using the 6th degree polynomial is going to be less than or equal to 1 times absolute value of x minus 0 to the n plus 1 be the 7th divided by 7 factorial. Okay, and so like that's our error, and we want that to be less than or equal to, so our error is going to be less than or equal to that, and we don't want that to be greater than 5 times 10 to the negative 4. So 5 times 10 to the negative 4. So cleaning this up a little bit, it looks like this now. I need the absolute value of x to the 7th over 7 factorial to be less than or equal to 5 times, I'm going to just write it like this so the times doesn't look like an x. I'm going to times everything by 7 factorial, so now I have absolute value of x to the 7th is equal to 7 factorial times 5 times 10 to the negative 4. Sorry, it's less than or equal. And then I'm going to, I need to raise both sides to the 1/7. All right, now it's time probably to go punch that into a calculator and see what we're getting. So I'll do that. I'm just going to use Desmos. I have it, I believe, pre-set up. And there it is. 1.141, we'll say. 1.141. Okay, so now just finishing off this inequality. Absolute value of x is less than 1.141. And so now, if you write it like this, that'll work. Okay, this is similar. If you look at the graphical technique we did in a previous video, it's kind of close, right? It's like a little bit different, but it's pretty close to the numbers we did when we did it graphically. All right, and so I think the big takeaway, if you got a little, if you got a little lost, this is somewhat of an advanced problem anyway, but just note that like what we're saying is that as long as you're restricted to the values of x between negative 1.141 and 1.141, you're guaranteed that that polynomial above is not going to be off by more than 5 times 10 to the negative 4.